Good afternoon, everyone. Today, I'm going to present GraphQ, Graph Query Processing with Abstraction Refinement. I'm Kai, a second-year PhD student from University of California, Irvine. Big graph is everywhere. Many domains use graph to encode useful information. The size of graph is becoming larger and larger. To give you an example, the total number of web pages in 2015 on the internet is about 4.6 billion, which is twice as the number of web pages 2 years ago. In order to efficiently process such big graphs, researchers design many graph processing systems. The existing graph processing systems all focus on whole graph computation, which is time-consuming. For example, using a 32-node cluster, it takes cliques, a distributed graph processing system, more than 30 minutes to do a whole graph computation over a 70-gig web graph for a very simple community detection graph algorithm. The whole graph computation seems an overkill for some real-world applications. Given a large graph, sometimes the user may only want to know information about a very small number of vertices and edges. Here are some real-world applications. For a navigation system, it's more important to quickly find one path with an acceptable distance between two locations than finding the shortest path. If you want to do target marketing, it's more important to find a target group of customers with a given property. It's not important to find all groups of customers. If you want to put ads online, it's more important to find a website with a very high PageRank value. It's not important to find PageRank values for all the web pages. These queries need iterative computation over graph vertices and edges, and we refer to these queries as analytical queries. Based on the real-world application, we have one observation. Many queries can be answered by exploring only a small fraction of the input graph. Driven by the observation, we want to ask two questions. Can we answer analytical queries efficiently by doing computation on partial graphs? If partial graphs are sufficient to answer the queries, can we process on a single PC without resorting to clusters? We follow the trend that advocates single PC-based big data processing, such as GraphG and Xstream, so that programmers do not need to worry about managing clusters. Driven by the two simple questions, we propose GraphQ, graph query processing with abstraction refinement over very large graphs on a single PC. Before I introduce GraphQ, let's talk about some background. Common to graph processing systems, the graph operated by GraphQ can be viewed as a direct graph. Each vertex and each edge has an associated value. Vertices and edge values can be modified. One of the most common programming models in many graph processing systems is vertex-centric programming model, which iteratively execute user-defined function on every vertex. The user-defined function describes the basic logic of the given graph algorithm. Each vertex computes the user-defined function in parallel. GraphQ is based on vertex-centric programming model. In each iteration for every vertex, read values from incoming edges, update according to user-defined function, and write values to outgoing edges. Now let's talk about GraphQ. Given a very large graph, GraphQ first divides whole graph into partitions. Each partition on a high level can be viewed as a subgraph. And in the initial phase, GraphQ computes local solutions on subgraphs without considering the interpartition edges. Ignoring the interpartition edges allows GraphQ to load one partition at a time and performs vertex-centric computation independently of other partitions, which will reduce the computation and I/O cost. Then in the check phase, GraphQ checks if the query can be answered. If yes, we finish. Otherwise, a refine phase is triggered to merge partitions to provide a broader scope of query answering. After the refine phase, the execution loops back to the check phase to check if the query can be answered again. As the refine phase progresses, small partitions are merged into big ones, and it's getting more and more difficult to merge partition into the memory, to load the partition into the memory. Continuing the search after the physical memory exhausted will involve frequent disk I/O and slow down the query performance. So we treat the capacity of memory as a budget, and we terminate GraphQ as soon as the merged partition cannot be loaded into the memory. Now let's talk about how to use GraphQ. Given an analytical query, usually in the form find data entities from the graph with a given quantitative property, the user first needs to find a related base application which performs the vertex-centric computation. And on top of this basic application, GraphQ provides some interface to define how the query can be answered. For example, if you have a query, find three cliques whose size is greater or equal than 5, the user can use maximum clique as a base application. And on top of the base maximum clique, GraphQ provides three interfaces to help the user to define how the clique query can be answered. And I will introduce the interface shortly. Given an analytical query, we want to answer the query as soon as possible by doing computation on partial graphs. So the goal of GraphQ is to select partitions to merge, hoping that the query can be answered by merging only a very small number of partitions. Then the challenge is how to select partitions to merge. We borrow the concept of abstraction refinement from program analysis to process graphs. There are basically two steps. In the abstraction step, we build abstraction graph to summarize the concrete graph. Abstraction graph serves as a navigation map for checking edge feasibility. And in the refinement step, we merge partitions, recover interpartition edges to provide a broader scope of query answering. Then the next question is, how should we build abstraction graph? We use abstraction function to build abstraction graph. The abstraction function on the high level can be viewed as a many-to-one mapping, which maps many concrete vertices to one abstract vertex. To perform a sound abstraction, we require to have some properties. All concrete vertices have abstract vertices. If there is no abstract edge between two abstract vertices, it is guaranteed that there is no concrete edge between any pair of the concrete vertices that abstracted by the two abstract vertices. Given a very large graph, GraphQ first partitions into small subgraph, and in the initial phase, GraphQ computes the local solutions and check if the query can be answered. If the query cannot be answered, the refine phase is triggered, and an abstraction graph is used to provide some guidance to select partitions to merge. As a summarization of the concrete graph, the abstraction graph is much smaller in size and can be always held in memory. In the refine phase, we have local results available. These local results have priorities. And these priorities are heuristic, can be customized by the programmers. Different applications may have different priorities. For example, for community detection, we may use the size of community as a metric for priority. Intuitively, merging partitions while larger community have been discovered is more likely to reach the goal of finding a community with a certain size. Then we select results with highest priority. However, simply only using this priority as a only guidance to select partitions will give you some false possibilities. Go back to the community example. It is possible that there's no connection between two communities with higher priority. So we can safely skip this option. So we use abstract graph to provide some guidance. GraphQ checks the existence of the abstract graph on the GraphQ checks the existence of the abstract edge on the abstract graph. The non-existence of abstract edge between two abstract vertices guarantees the non-existence of any concrete edges between any concrete two vertices abstracted by the two abstract vertices. After check the abstract graph, GraphQ selects partitions to merge. Merge means load partitions to memory and recover interpartition edges, which I ignored before. After merge, we have a larger partition, and we can do the vertex-centric computation on this new partition. And we have a larger scope of query answering. Now let's use a very simple example to better illustrate GraphQ. This small graph has 9 vertices. GraphQ divides it into 3 partitions. The vertices in the same color belong to the same partition. The solid line represents intra-partition edges, and the dotted line represents inter-partition edges. According to different abstract function, we may have different abstract graph. In GraphQ, we use interval domain to abstract concrete vertices, which means vertices with consecutive labels are abstracted by the same abstract vertex. The reason we use interval domain is for the data locality, meaning that concrete edges which are abstracted by one abstracted edge are physically located together. In this small example, we use one abstract vertex to represent 3 consecutive concrete vertices, and we build the abstract graph. And after the initial phase, we have 4 local cliques, and we want to ask if there is a clique whose size is no less than 5. And after the initial phase, we have 4 local cliques available. And we want to ask, is there a clique size greater or equal than 5? The answer is no. And the size of clique decides its priority. Based on the priority, GraphQ first inspects 2 cliques with a larger size, 1, 2, 3, and 7, 8, 9. GraphQ checks the abstract edge on the abstract graph. As there is no abstract edge, then we can safely skip this option. Then GraphQ tries to check 1, 2, 3, and 4, 6. And there is an abstract edge on the abstract graph, so it's possible we can answer the query. Then GraphQ merges partitions A and B. Merge means recover the interpartition edges, which I ignored before. After merge, we have a larger partition. And we do the computation, and we have a new clique, 1, 2, 3, and 4, 6. GraphQ works for a class of queries with monotone update functions. There are 2 reasons. First, it will give you correctness guarantees. Second, As the merge progresses, you will find better solutions in the forward execution. We have a formal analysis in the paper. If you are interested, please refer to the paper for more details. GraphQ cannot answer all kinds of queries. For example, for belief propagation, the probability in a vertex may fluctuate, which prevents the user from using GraphQ. Our implementation is based on GraphG, which is a single machine graph processing system. And the details of the implementation are in the paper. We have done experiments over real-world large graphs on a single PC with 10 gig RAM and 256 gigs SSD. And we use two graphs, Twitter 2010, which is a social network working graph, and UK 2005, which is a web graph. We have implemented 5 queries and have conducted 3 sets of experiments. First, we performed queries with various goals. We want to find data entities with a given quantitative property to understand the query processing capacity. Second, we compare the query answering performance between GraphQ and modified GraphG. We modify GraphG to terminate as soon as the query can be answered. Third, we vary abstraction granularity to understand the impact of abstraction refinement. How to make queries? We run whole graph computation on GraphG and get all results. And then we select top 100 values. We divide it into intervals. Each interval has a lower bound and upper bound value. We generate 20 queries for each interval. And each query has a random value which falls into this interval. The first experiment is to perform queries with various goals. This slide shows the performance for PageRank queries over UK 2005. We divide top 100 PageRank values into 4 intervals. In this figure, x-axis represents how many vertices we want to find. Y-axis represents the running time of GraphQ. And the leftmost bar shows the whole graph running time on GraphG, which is more than 30 minutes. We can see that for all the queries, GraphQ can answer the query much faster than GraphG. And if you want to find less entities with lower goals, it's very helpful to use GraphQ. If you want to find more entities with higher goals, the running time is becoming longer. The second experiment is to compare GraphQ with modified GraphG. We modify GraphG to terminate as soon as the query is answered. This slide shows the performance for community detection over Twitter 2010. The x-axis represents the intervals of the top 100 community size. The y-axis represents the ratios between the running time of modified GraphG and GraphQ. We can see that the GraphQ, which works on partial graph, outperforms GraphG, which works on the whole graph computation. And the delta represents how many communities we want to find. The third experiment is to vary abstraction granularity to understand the impact of abstraction refinement. We vary the abstraction granularity by A equals 25, 50, and 100, where A represents the number of abstract vertices used for each partition. The higher A is the finer granularity. The x-axis represents the intervals of top 100 PageRank values. We divide it into 5 intervals. The y-axis represents the running time of GraphQ. We can see that the finer granularity, the better performance, the shorter running time. And we also compared GraphQ without abstraction refinement. Partitions are randomly merged. It is interesting to see that in some cases, the random selection is better than A equals 25. The reason is that the abstraction level is so high that the partitions are almost sequentially merged. So in this case, the random selection has a higher priority, has higher probability to select proper partitions to merge. To conclude, I present GraphQ, a graph query process answering system based on abstraction refinement. The experiment results shows that it can efficiently answer analytical queries over partial graphs. It opens up new possibilities to scale up big graph processing with small amounts of resources. And that's it for my presentation. Thank you.